I hope you are not too tired at the moment, and maybe not too hungry, but try to sort of conclude this morning session. So first of all, thanks to the organizer for this very nice workshop and the program, of course. And yeah, thanks for the opportunity to speak here. Actually, my talk will be a bit more abstract and not really related to direct applications, and mainly because I focus my research on sort of numerics and analysis of 2D models of turbulence. So in particular, the talk will be about the Euler equations on the sphere in this case. So of course, all of you have in mind applications for this kind of model, but actually it's not direct applicable, or it's not like it doesn't have a direct impact on climate science. Anyway, so the title of the talk will be on the infinite dimension limit of invariant measures and solution of Zeitlin to be evaluation. Non-Python. So this is a joint work with the Professor Franco Flandoli and Umberto Papaletta. And this work is going to appear in the Journal of Statistical Theories, probably this year. Okay, so so the idea is to consider the 2D Euler equations in the vorticity formulation. So the vorticity is the scalar field for 2D fluids, which is given by in general by this formula. So the projection is n. The projection of the curl of the velocity field of normal of the surface. So in our case, we will mainly deal with the sphere. This is the normal field, and this is our surface. Okay, and these equations have, of course, a form that you have seen several times. So in general, we can write using the notation of orthogonal gradient of the string function times the gradient of the vorticity, and string function and the vorticity are related by Poisson equation. But actually, for some sort of more geometrical reasons, I prefer to write these equations in terms of Poisson brackets, which are exactly defined in this way. And actually on the sphere, you can bring it also more explicitly if you want. So this is a model for incompressible, invisible, homogeneous fluid. So it's very ideal model. But what is actually relevant is that this captures a lot of the dynamics of a fluid, and in particular, even if 2D models are, of course, a very sort of rough approximation of real fluids, at least for geophysical purposes, they are still important because of stratification and because of the different scales between horizontal scales and vertical scales. So we can still learn a lot from these equations. And mathematically, they are interesting, in particular because they have infinite conservation laws. Number of conservation laws. And in particular, we have the Hamiltonian or the total energy. And depending on the symmetry of the Hamiltonian, can have some momentum. So, for example, the sphere, the angular momentum, which are 3 components. And in particular, then we have the Casimir functions, which are defined as the integral on the surface of the vorticity for any f C1 function on R. So these are Casimirs. And this.
Sorry, why do you call these Zeitlin equations? I mean, there's for instance, a paper by Henry McKean that goes back to, I don't know when, which states all the.
No, but these are not the Zeitlin equations.
Oh.
No, the Zeitlin equation will come later.
Oh, okay.
Yes. Now this is just a regular Euler. So this is just a regular Euler. In fact, actually, the Zeitlin model appears because we want to study these equations numerically, retaining these first integrals, right? So that's the origin of Zeitlin model. Most of this standard discretization, like spectral discretization of this equation, does not respect higher order Casimirs. But Zeitlin model is the sort of, as a mathematician, the most geometrical way to discretize these equations. And and why do we want to conserve these first integrals? Because conserved quantities determine the long time behavior of the fluid. So I stated here like 2 main challenges to understand the Euler equations. So 2 challenges. So the first one, I call it like direct analysis of the Euler equations. And to do so, we want to use or to exploit direct numerical simulations of the Euler equations. And the second challenge is to study or sort of elaborate a theory for the statistical mechanics of the Euler equations. And the problem of a theory for statistical mechanics of the Euler equations is actually related to the fact that we have infinite amount of conservation laws. And so the idea is actually to show that we can use numerical analysis and numerical simulations, not only for a direct analysis, so direct simulations of the Euler equation, but also for studying or to develop a statistical mechanical theory for the Euler equations. And so this origin, actually, the study of statistical mechanics for fluids actually dates back from the 40s from the work of Gonzaga, at least, in 1949, for the point vortex model. So the idea is that we would like to have, let's say, following the idea of statistical mechanics, also the procedure that Gonzaga did. So we would like to define a Gibbs measure of the form, that's right here, of the form mu of some d omega, which is the vorticity, and then you will have exponential minus alpha h omega minus beta with some Casimir function omega d omega, and this should be the vague measure on the space of vorticity. So I don't come from the probability community. So this was a work that was introduced by Franco Flannery and Umberto Lavalletra. And the problem is that this is just a formal measure that maybe can be seen in or can be used by physicists, but actually in mathematics this measure is not defined in this form. So the idea is that we actually want to define the global Gibbs measure, but there are problems. So in particular, up to now, no one was able to construct such a measure where when f is not a quadratic function. And the idea is that actually, I will show you in a moment, maybe the Zeitlin model can help us to solve this problem. So the idea is that, okay, we can't define a Gibbs measure, so an invariant measure for the Euler equations directly, but if we pass to a finite dimensional model, so in this case the Zeitlin model, which is actually usually used for numerical simulations, we can also infer some information from the infinite dimensional equations, and in particular we can infer something on the measure. So so that the model, so let's take some properties. So works or can be defined for any compact surface. S symmetry, at least orientable, let's say, and retains the geometry Euler equations. Okay, so how actually it is defined? So Zeitlin model, so this dates back from the 90s actually. Takes a vorticity field, so let's omega be our vorticity, let's take it regular for the moment, so smooth function on the sphere, and then it maps the vorticity to a matrix omega, which lives in the space of skew permutation matrices, which is denoted by SUN for any n larger or equal than 1. Now recall that SUN is defined as a matrix in Cn such that a star is equal to minus a, and the trace of a is equal to 0. Okay, and then we also have a dynamics for this matrix, which is actually given by replacing the Poisson bracket with some commutator of matrices, and the Poisson equation is discretized by a scriptable discrete Laplacian. So the form of the equations is equivalent to the one of the Euler equations. So this is exactly right as the Zeitlin equations. And the properties of conservation of, or the conservative discretization of Zeitlin has this conservation law. So an analogous of energy, which now replaces the integral by the trace operator, and an analogous for the Casimirs. So actually, we can define CF of W as the trace of F of W. So now the idea is that actually here we are on a finite dimensional system, because SUN has dimension n squared minus 1. So actually it is well defined for any Casimir and the energy itself, a measure that we can call it mu of n, or let's call it mu of n of the W, and now the direct measure is well defined. And this is defined as E semi minus alpha h of W minus beta CF of W dW. So this measure is well defined. And the idea is,
sorry, what was the restriction on the Casimirs before you did this? You said something, but I didn't hear well.
here.
Yeah.
Oh, yeah. So the restriction, so these measures can be defined for f quadratic. So for the enstrophy, let's say. So the usual coupling is energy enstrophy invariant measures. Of course, these are the most important one, but this is still like something that is actually very interesting, because at least from my point of view, that these equations, the Euler equations, are known for very long time, of course, since Euler, at least. And still the role of higher order Casimir is not well explained. So we actually don't know how, we don't know for certainty that only energy and entropy are to be considered. And this is passing both in terms of mathematics and physics, of course. And I think this is a very central question to investigate.
Can I ask a question?
Yes.
So when you have this, the Casimir as a arbitrary functions of Casimirs in the integral in the continuum case, but in the discrete case, since you have discretized, there can only be a finite number. So
Yeah.
I don't quite. So how can I see that? Because f, you can't take any. I mean, in the end, there need to be a finite number. So
That's correct.
So which functions remain? Is that some polynomial?
Yeah.
Why is it some finite polynomial? I suspect, right?
That's correct. So actually, these are independent. You can take a basis for these conservation laws. Let's say for k, it goes from 2 to n. And then we define the ck of w as the trace of w to the power k. And these are independent.
So that means that in your measure, your beta there and the CF is probably k quantities, is that right? So you have the energy then, and then these k discrete Casimirs, each, so probably beta is a factor of some kind.
Yes.
Okay, just to be sure.
Yes, that's correct. Yes. Yes, in fact,
So you have k plus 1 conservation laws you put in your measure. Is that correct?
yeah, and saying that, but yes, but
N plus 1.
yes, that's correct. Of course, the higher the Casimir is, the worse the approximation of the Casimir. I mean, of this finite model, right? So, for example, enstrophy is conserved, is always well preserved, but then that cubic Casimirs also have some sort of tail in terms of Fourier modes that are not well approximated. But in the limit, if the vortex is sufficiently irregular, then we have the Casimir converges to the original one. And actually, for example, something that is conserved in the original Euler equations is the infinite norm as well, and we have some bounds also for the Zeitlin model of the infinite norm. So the infinite norm of the original vorticity is controlled by the spectral norm of the discrete vorticity. Yeah. So okay. So the idea then is. So one of the point now is to look at the limits for mu n going to something in the limit of n going to infinity. So, and of course, I didn't say here, but the Zeitlin model, of course, approximates the original equations. So, in particular, if I take the bracket of let's say PW minus actually now the projection Pn of the original brackets, this in the spectral norm of matrices, this goes like O to the n minus 2. So it's a quadratic convergence for n going to infinity. Okay, and using this fact, so using the fact that the Zeitlin model approximates the original equations, we would like to understand the limits of the measure, invariant measures. And maybe I don't have much time. But let's state at least some results in the paper. So the paper mainly focuses on the most simple or the simplest possible invariant measure one can think, which is the enstrophy measure. So we take as Casimir f equal x squared. So this is something that I think is expected, and it's actually new for the Zeitlin model, but it's not new in terms of sort of approximation of invariant measure for the Euler equations. So the enstrophy measure. So it's defined on the space of matrices as like this, and so we define then the right inverse of the projection, which is the injection from SUN to C infinity S2. So from the discrete vorticity, we get a continuous function which is exactly iota n of W. And then we can define the pullback measure on this space. We define mu n as I iota star n mu n. And then we have then the result here. Then we have mu n weakly converges to mu, which is actually the enstrophy measure on for let's say for the Euler equations. So you can think as a Gaussian measure defined component-wise on each component of the vorticity expressed in terms of spherical harmonics in this case. And the support, the interesting thing is that the support of nu is actually on this quite large space, GH-1 minus of S2, which is defined as the intersection for any epsilon larger than 0 of H-1 minus epsilon S2. Okay, so now we have the entropy measure. So as mu is invariant measure for the Euler equations. And we can prove that as a stationary stochastic process distributed as mu is actually approximated by the solutions of the Euler equations of the Zeitlin model distributed as mu n. But now the problem is we would like to define other invariant measures. We would like to take, for example, e to the minus to the power 4 of omega, and then nu d omega. So this, what is this object? So this is the question. So for example, if you want an invariant measure with a quartic Casimir, the problem is that on the one hand, this object is not defined here because here we are on distribution, so the fourth power of the distribution doesn't make sense. And we can't use any result on Gaussian measures because this is not Gaussian. So the idea is that maybe we can infer something from the Zeitlin model. So we take the trace of the fourth power of the discrete vorticity, and then as a measure we have mu n of dw. And then we want to look at the limit for n going to infinity of this quantity and see and check whether we can get something reasonable. And the idea is that here some magic can happen, and it's called sometimes renormalization. So when you subtract the different infinities, because we expect this quantity to diverge, and you get some finite limit. And I stop here because it means a bit late. But the idea is that maybe finite dimensional models like Zeitlin model, but one can take other models, for example, can tell us how to approximate these objects which are not actually defined in this form for the original Euler equations. Thank you very much.
Questions? Comments? So just curious, what you call Zeitlin model is basically any numerical scheme that conserves Casimirs?
Not any. So Zeitlin. So the problem here to define Zeitlin model is to get this map from here to here, this projection from the infinite dimensional space of the infinity S2, let's say, to some finite dimensional metric space. The Zeitlin model is something that actually somehow approximate what are the original Poisson brackets with some finite dimensional bracket, which is this matrix commutator or Lie bracket. And yeah, so in principle, you might have different algebraic structures. So the Poisson brackets could be different. And then if you manage to find a finite dimensional approximation with Lie brackets, then you will have another, let's say, finite dimensional model which replaces the Casimirs. So for example, there is a Zeitlin model for a two-layer quasi-geostrophic equation. And because the Poisson structure is different, but then you can relate that Poisson structure to some finite Lie algebra structure. So to answer your question, I would say that Zeitlin models are approximation which transform infinite dimensional Poisson structure to finite dimensional Lie brackets. At least this is my point of view. And why this is important? Because once you have the conservation of the geometry behind, which is the bracket, then you have also conservation laws that are automatically preserved.
Thank you.
Yeah, I wanted to know what is actually this mapping.
Oh, this mapping is given, but if you have the vorticity, you can read, for example, on the torus, which is simpler to define, but on the sphere, basically you write your vorticity in terms of spherical harmonics. And then what you do is that you can find, and this is very complicated, actually, theory from actually it comes from representation theory. You can find some finite dimensional matrices. You replace the spherical harmonics with some matrices TLM, which are defined for L, which goes from 1 to n, and n which goes from minus L to L, which somehow resemble the spherical harmonics. So these are called sometimes spherical matrices. And in particular, they share the same orthogonality with respect to the Frobenius inner product. And they resemble the somehow the bracket. So that if you take the bracket of two of these matrices, then in the limit for n going to infinity, the structural constants converge to the bracket of two spherical harmonics. It's like when you see it the first time, it's like magic. Having this kind of matrices is not trivial at all, and it actually, relies on representation theory and complex geometry results. So it's called actually quantization, and this is some procedure that is done in geometry when you want to study infinite dimensional spaces like spatial functions on the sphere. You sort of can approximate your spatial functions with the finite dimensional one, which resembles the original one. So, yeah.
A comment, as there is work by Andy Maida, and they find that higher order Casimirs beyond the enstrophy probably are not very important for the large scale flow, as they simply hardly affect the large scale flow because they are so concentrated in the higher wave numbers. You know this work where they have this Gibbs measure constrained by energy entropy, and then they use this McLachlan scheme which conserves higher order Casimirs, and then they try has an effect on large scale flow or not. And they find beyond entropy it's not important. It has hardly any effect.
Yes, I know that work, and actually that is based on Zeitlin model, in fact, on the torus. But for example, this work of Jason Frank, and which says something different. So it's not. It really depends on the model you use probably. And if I remember correctly, that work of mine doesn't have very high resolution as well. So of course, it's the energy and entropy are the most relevant ones. But for example, there are statistical mechanical theory like the one of the MRS theory, called the Miller-Roberts and Superiore theory, which they take into account all the Casimirs. So for them, they are statistically relevant somehow. So I of course, that work of mine is important because it says something, But I don't think it's like definitely answer to this question.
The last question by no.
I'll ask it in person.
Okay. Last question. Yeah, Michael.
Well, it sort of reminds me of ordinary interpolation. You know, higher order polynomials are not good for interpolation because they're oscillating.
Yes.
So that's why people came up with splines. And the question is, you know, would there be some counterpart to splines in spectral space and something like that? You know, some weighted things in the lower Casimirs that do a better job than the higher Casimirs. That's sort of a vague idea.
That is a very interesting question, but
Well,
I can answer it. I can answer this. You can. The only thing I can say, maybe it's not relevant, but maybe yes, is that this is a choice for Casimirs. The other natural choice is eigenvalues of W. So if you take the eigenvalue of W, this is another basis for Casimirs. And actually, it's interesting, and this is in one of the appendices of the paper, they correspond somehow to the Kelvin circulation theorem. So conserving the Kelvin circulation theorem. Yeah. Yes, exactly. So conserving the eigenvalues of W somehow resembles the fact that in this finite dimensional model, we have proxy conservation laws for the Kelvin circulation theorem. And maybe these actually are better than these Casimirs. And they are more natural somehow. And these are a combination of lower order Casimirs. So maybe this is how.
Yeah, so it's maybe within the functional calculus that you can find the appropriate counterpart of, you know, of splines.
Yeah, that's a hope, of course. Yes.
Okay, thank you very much.
Thank you.
Presenters this morning, and we resume at 2 p.m. Right?
Yes. One more comment, just a reminder that we have discussions in the final session today, and that you have an opportunity to steer these discussions in the way that you want to by submitting suggestions for themes via the website. So we go to the header workshop 1 discussion themes. There you can submit suggestions if you wish.
I need to give you my thought. I'm not so sure that I